So in this video, I want to go into matrices and vectors. First of all, describing how a vector can represent a function or a signal, and then understanding matrices as collections of vectors. In other words, collections of functions or signals or even images, where we can visualize what each column and each row looks like. And then having done that, I want to look into how matrix vector multiplication works. What is a way of visualizing matrix vector multiplication beyond just memorizing the way of doing it? So let's take a closer look. So we have a continuous function here, f of x. So f as a function of some independent spatial variable x. And then we might have a discretized version of the function, which I'll denote here with f square brackets x. So now x would be some kind of index to the function f. And there I'm showing 15 or so values, sample points. And at each of these sampling points here along the x-axis, I will collect some value of the function. And so here I'm assuming it's just a set of numbers that I've sampled, which in fact is a list of numbers. And if we've got a list of numbers, then we have a vector. Now, normally vectors are in column form, like I'm showing there. But if I put them along in a row like this, then I'm putting a superscript T for transpose there, to say that that is indeed that. So transpose just means change between column and row format. So we could refer to this vector as just a bold letter like F for all of these elements in the vector. Or we could try and capture it as some kind of discrete function like this, but obviously there's only a limited range of these indices x to look up a particular element f in the vector. And then if we wanted to refer to a particular element of the vector, then we could use some kind of subscript, some kind of index I to access any of the elements in the vector f, or indeed we could keep our f square brackets notation, where now we supply a particular choice of index for which to find the value f. You know, here loosely it's implying that x could take on any value, and so there loosely we're referring to the whole of the vector. Okay, so that's what vectors are like. What about matrices? Well, you're probably familiar with matrices as being effectively a 2D array, a grid of numbers. But I want here to show them in a way that links them to signals, images, functions, and indeed, therefore, vectors. So what we're going to say is that each of the rows of a matrix is a vector. So therefore that could be a sampled signal or a sampled image just unrolled into one long line of numbers. Or indeed the columns could also be regarded as vectors. Okay, so again that's just a list of numbers just stacked in a column. So if we do that, then a matrix then, in general, will have a number of rows. So here I'm showing row 1, row 2, a general row I, all the way up to row capital I. So I'm saying there are capital I rows in this matrix. I'm just giving an arbitrary example here. And for each row, we have, as seen before, a signal or an image, because it's just a vector. It's just a list of numbers. And we can use a list of numbers to represent an arbitrary signal or an image, whatever it is that we're interested in, such as a sampled function. Now, to notice, of course, that in each one of these row vectors, okay, we have a number of elements, a number of samples, which in fact corresponds to the number of columns in the matrix. So I'm labeling that first column as column 1, column 2, an arbitrary column j, right up to capital J as the last column in this particular matrix. And that shows us how many elements are in each of those row vectors. But as we know, each column can be regarded as a signal or an image, because each column is a list of numbers which is a vector. And of course, therefore, there are going to be how many elements in each column? Well, there are going to be as many elements as there are rows in the matrix. So therefore, I equals 1 to capital I elements or samples in each one of those column vectors. And so this 2D grid of numbers, which I've been describing as collections of vectors, we're going to call typically a bold uppercase letter A, and we're saying that's equal to a set, that's the curly braces here, a set of values, Aij, where I refers to the row number and J refers to the column number, and so Aij will allow us to access any or refer to any of the values inside the matrix. And here I'm using capital I times capital J to denote the fact that there are capital I rows and capital J columns in our matrix A. Okay, so we've done vectors, we've done matrices. Now what happens if we use a matrix to multiply a vector? So here's a matrix A, just an arbitrary example again, just full of various numbers. So that's A, and then this is our input vector X, just a list of numbers. That's going to be equal to some output vector Y. Now, of course, we all know the standard formula for how to find this output vector, but I just want to go into that in a bit more detail here and try and visualize what's happening. But again, just to notice the notation here, this, if you like, is our matrix A, our system matrix. Here is our input vector X, and here is our output vector Y. So first off, we'll do what I call a row-based understanding of matrix vector multiplication. So that means we're now considering a row of the matrix, okay, and that's going to be a row vector R, and that delivers this output here when that row vector is in scalar product or dot product with this input vector X. So it's a vector R, which is just a row of the matrix, dot product with the input vector X. That means we're taking 0 times 3 plus 2 times 1 plus 3 times 5 and so on all the way up to 2 times 1. And so that process is none other than the scalar product of two vectors. And so here I'm showing that what we're doing is a pointwise multiplication of a signal or an image or a function that's been sampled, a pointwise multiplication of one image or function with another image or function or signal. It's a point-by-point multiplication and then summing together the outcome of that product of two signals. And the outcome of that is going to be a scalar value, which I'm labeling here as y1. So as mentioned, it's the scalar product of two vectors. The output here is a scalar value, the first element here for this output vector y, and it's equal to the row vector r in dot product with the input vector x. And so standard notation then is to say that that's just exactly that process I described. It will be r1 times x1 plus r2 times x2 and so on, all the way up to capital J, which is the number of columns. And of course, that also means that our input vector needs to have as many elements as there are columns in the matrix in order for matrix vector multiplication to be valid. And so here I'm just spelling out the fact that that scalar product of that row vector and that input vector x, actually what we're doing is taking here, in this instance, the first row of the matrix. So I'm using that, I'm denoting that as A1 for row 1, and then I'm considering all of the columns of that single row 1 with all of the elements xj in vector x. And again, when I do the point-by-point product, I've then got to sum up the overall result of that product. And then for some arbitrary output value, output element in the output vector y, we have this expression, which is really the standard notation for matrix vector multiplication. We're saying that yi is, if you like, the row vector ai, and then you're going along all the columns indexed by j there, corresponding to each of the elements in the input vector x. You sum those all up, the products of those two vectors, scalar product, in other words, to get the output value yi. So let's visualize that again. So this is an example input vector x, which here I'm just showing a 5-dimensional vector, just capturing 5 samples of some function, some signal, or even a 5-pixel image, if you like, which could be rearranged into a 2D array. It's quite awkward with only 5 pixels, but you get the idea. It's just 5 values. Okay, so I'm just denoting that here for the case of a 1D function sampled at 5 points to give us that 5D vector. Okay, so that's this x. And that's going to get multiplied point by point by some other signal or image or sampled function, which is going to be contained within some row I of that matrix A. Okay, so I'm reading across row I of matrix A, and that's giving me some 5 sample points, which again should be interpreted as a signal or an image of some sort, or a sampled function. So we do a point-by-point multiplication. So it's function times function multiplication. So that'd be like 4 times 1 gives 4, 5 times 0 gives 0, and so on up to the last element, 5 times 0 gives 0. And so here we get this product, which is also a signal or an image, which we then sum. We sum all of the elements in there. So in this example, that gives a value of 14. And that is what gives us the overall output, in other words, the output element yi for the case of row I of the matrix, which has just been a scalar product of the input vector and row I of matrix A. So again, that's just written in that notation, which is no different to the standard notation I've already shown on the previous slide. It's just that I've highlighted here that AI is like referring to row I of the matrix A. Okay, so that was the row-based understanding. I think it's also useful to look at a column-based understanding. So again, here's our matrix A, and there's our input vector X, output vector Y. And now again, I'm emphasizing that those columns could also be interpreted as signals, images, or sampled functions. And now, you see what I've done there? I've taken the input vector x, and I've just, for illustrative purposes, placed each of the values along the top of the matrix there. That's just for illustrative purposes. It's not a standard way of doing it. So all I did was just take those values, place them along the top there to indicate that we can consider matrix vector multiplication as taking the input vector x as a set of weighting factors or scale factors for each of the column vectors contained in the matrix. So in other words, we just read off all the values there, and so for convenience I've put them along the top there, but I'll just remove them there because it's not standard notation. So it acts as a weighting, they act as weighting factors for each of the column vectors, and then as you can see there, I'm just taking that weighted set of column vectors and adding them all together to get my one single output vector. So it's a bit like doing those scalar products all in parallel, if you like. So that's what I'm denoting here. I'm saying the output vector y is just equal to the column vectors. Each of the columns I'm denoting here as Cj. Okay, so that's just one column of the matrix A. And then I've got a weighting factor xj for each of those columns, and then I sum together that set of weighted columns to get my overall output vector y. And there I'm trying to denote that in something closer to the standard notation, and here I'm using a dot to denote all the elements in column J of matrix A. But don't worry so much about that notation. Again, I'd prefer that you stay with the standard notation, which I'll show again on the next slide. Okay, so there is the standard y equals ax notation, or indeed this is also a recognized standard notation where we're saying that some output element I of the output vector y is just equal to the aij xj summation that we've seen now in two different ways on the previous slides. I also want to point out here a very useful way of checking equations to make sure that all is well. notice here that our summation is over the columns, okay, of the matrix. It's over this second index, which I'm labeling as J. And of course, that has to agree with the index for the input vector, because we know that's a set of weights for each of the columns in A. And so when we're summing over that index J, then notice that J, that should read J here, does not appear on the left-hand side of the equation. We're summing it out when we do this summation, okay? And all we're left with is that I, okay? So that's to clarify here that there's no sum over this index, so I appears on the left-hand side of this equation, okay? Because we're summing over J and we've left I behind, therefore I is what appears on that left-hand side. So in review, we can use a vector to represent a function or a signal, and we can understand matrices as collections of functions or signals, where each row or each column could be a function, a signal, or even an image. And then we can also begin to understand matrix vector multiplication in two very key ways, either the row-based understanding involving scalar products, that's taking a function, point-by-point multiplication with another sampled function, and then you sum together the result to get the output element, the scalar product output, or indeed column-based understanding, where you take the input vector as a set of weights for all of the matrix columns, which you then add together to get the output vector. Thanks for listening.